Hi! With a naive approach, simulating a 62-spin quantum system would require 2 × 10 to the 28 gigabytes of RAM, which is quite a large number. And this is just the storage needed to save the system state. In certain situations, however, we can use a clever trick to reduce the amount of RAM needed. So in this video, we will discuss such a situation and show how to use HQS Quantum Solver to simulate the system. Let's have a look at the system we're going to simulate. We start with a quantum Heisenberg model, which consists of a chain of spins. Neighboring spins on the chain interact. We pick the antiferromagnetic case, which means that neighboring spins want to align in opposite direction of each other. The next ingredient is a magnetic field. The field is homogeneous and points in negative z direction. The effect of the field is that all spins are pushed towards the negative z direction. The final ingredient are a large number of surrounding spins that interact weakly with all the other spins. Since they only interact weakly, the magnetic field dominates, and we expect only a slight excitation in the positive z direction for the surrounding spins. This fact is key to making the simulation possible on a laptop. The next step in creating the simulation is to write down a mathematical description of the system. The mathematical description is given by the Hamiltonian of the system, which looks like this. Here, we label the spins in the Heisenberg chain from 0 to n1-1 and the surrounding spins from n1 to n2-1. Let's have a closer look at the Hamiltonian. The Hamiltonian consists of 3 parts. The first part describes the magnetic field. The real variable B determines the strength of the field in the z direction. The operator SZJ is the observable of the spin in the z direction of particle J. The second part describes the strong interaction of the Heisenberg chain. The variable J strong determines the coupling strength. The boldface Sj is the spin vector operator. We sum over the scalar product of the spin vector operators of neighboring spins in the chain. Since the term has a positive sign, it is energetically favorable if the neighboring spins face in opposite direction. The third part describes a weak coupling between all the spins in the system. We sum over all pairs of spins where the coupling is determined by a randomly chosen matrix. The variable J weak determines the overall strength of this part. If we were to naively try to simulate the system, we would quickly run out of memory. However, since we only expect a slight excitation in positive z direction for the surrounding spins, a clever choice of the vector space the Hamiltonian is defined on reduces the amount of storage needed. Note that in quantum mechanics, the vector space of the Hamiltonian is determined by the state that the system can be in. We pick 2 spaces. The first space, V1, corresponds to all the possible states that the Heisenberg chain can be in. The second space, V2, corresponds to all the states where at most one of the surrounding spins is in the up state. We get the space of the Hamiltonian by taking the tensor product of the two. With this choice, when we increase the number of particles in the chain, the dimension of the vector space grows exponentially, but if we increase the number of the surrounding particles, the dimension only grows linearly. This allows us to simulate systems where the number of surrounding spins is large. With the Hamiltonian in place, we can now look at how to program the simulation. We will write the simulation using Python and HQS Quantum Solver, the latter being a Python library that provides, among other things, easy ways to assemble quantum mechanical operators. Note that you can download the entire code as a Jupyter notebook using the link in the video description. The purpose of this simulation is to compute the energy levels and expectation values of the ground state polarization of the system. We start by making the necessary imports. We shall not go into detail here, since we will explain them as we move along. Next, we define the parameters of the simulation. The variable size part 1 stores the number of particles in the Heisenberg chain. The variable size part 2 stores the number of surrounding spins. The variable B stores the strength of the magnetic field, and we set the magnetic field to a negative value to make it point in the downward direction. Finally, the variables J strong and J weak store the interaction strength of the strong and the weak interaction, respectively. In order to compute the desired quantities, we first need to construct the Hamiltonian of the system, which in turn requires to define the vector space that the operator is defined on. The space is constructed like this. The space that we want to define is the tensor product of the two vector spaces v1 and v2, which is computed here. The space v1 is constructed by this line of code. As you can see, the space is defined by creating an instance of the vector space class and providing the size and total spin z attributes. Size defines the number of particles in the system. Total spin z can be used to restrict the states represented by the space to states with a given total spin polarization in the z direction. Since v1 is supposed to include all possible states, we just provide all as an argument. The space v2 is defined by these lines. The space v2 corresponds to all the states where at most one of the surrounding spins is in the up state. We build this space by combining two spaces. Note that the states where all the spins are in the down state is characterized by a total spin polarization of minus the number of particles divided by 2. And the state where exactly one spin is in the up state is characterized by a total spin polarization of minus the number of particles divided by 2 plus 1. We create a vector space for each of these spin polarizations. Since the argument total spin z is given in units of 1/2, we have to multiply the desired value of the total spin in z direction by 2. We combine the two spaces using the pipe operator to obtain the space that represents the union of the states that the individual spaces were representing. Having constructed the vector space, we can now build the Hamiltonian like this. The construction of the Hamiltonian operator happens here. The operator is constructed by instantiating the operator class while providing the mathematical term describing the operator and providing the vector space the operator is defined on. Note that the interaction term maps onto states that are not part of the vector space V. Thus we have to pass strict equals false as an additional argument to allow for these states being ignored. The mathematical term describing the operator is created by calling the magnetic field Z and the isotropic interaction functions. The former describing the magnetic field, the latter describing the spin interaction. Both of these functions take coefficient vectors or matrices as input. Let's have a look at the magnetic field Z function. The function expects a vector which gives the strength of the magnetic field per particle position. To get a constant field across all particle positions, we need to create a constant vector filled with the magnetic field strength. Which is the purpose of this line of code. To define the interaction terms, we use the isotropic interaction function. The function expects a matrix that describes the interaction strength for each pair of particles. To describe the particle chain on the first n1 particles, we need to construct this matrix. This can be done using the Dirac function of NumPy. To model the weak and random coupling, we need to construct another coefficient matrix. We create a strictly upper triangular matrix with entries in the appropriate range by these lines of code. Having constructed the Hamiltonian, we can now, for example, plot the energy levels of the system as follows. The energy levels are the eigenvalues of the Hamiltonian. We use the SciPy EIC function to compute the 20 smallest eigenvalues and hence energy levels. Note that we are directly passing the quantum solver operator to the EIC function. This is possible because quantum solver operators implement the SciPy linear operator interface. Running the code should produce this plot. Another interesting quantity is to look at the expectation value of the spin polarization of the ground state. Let us define a function that computes the expectation value for each particle. This code first constructs a list of spin z operators and then defines a function that computes the expectation value for each operator. The function directly implements the formula for the expectation value. We can then use matplotlib to plot the expectation value. If we run this code, we should see this plot. With that, we conclude the video. If you want to have a closer look at the code, check out the Jupyter Notebook link below. To run the code, go to cloud.quantumsimulations.de to request the free trial version of HQS Quantum Solver. If you enjoyed this video, leave a like and consider subscribing.